Thank you. All right, page 12. We're going to look at implicit differentiation. So we need to know the difference between an explicit equation and an implicit equation. So an explicit equation is one that is easy to get y by itself. Like y equals 3x squared minus 2 is a parabola. An implicit equation still has the relationship, but isn't necessarily written y by itself. In fact, if I tried to change this circle, x squared plus y squared equals 16, and if I tried to get y by itself, you see that you'd have to first move the x squared over to the other side, and then you'd have to square root both sides. You get plus or minus. And it's not a function, because the plus one would be a function, the minus one would be the function, but together, they're not a function. So some things cannot be written as explicit functions. It's impossible to do that because they have more than one option. But you could consider all of the options. And so we have something called implicit differentiation to help us figure that out. And we just watched a video. I'm going to show you another way of thinking about the same thing from the video. And I mean, I'm biased. I like my method even better. But this is what we're going to do for figuring out implicit differentiation. You have x squared plus y squared equals 16. And you're going to imagine you could do exactly what we did here. But sometimes we won't be able to. But you're going to imagine it's possible to get y by itself, even if you can't. Okay? So now, what we want to find is we want to find the derivative. Our notation for finding the derivative, right? We want, and we'll use Leibniz notation, we want dy dx. We want, wow, what a good day. There we are. I was already thinking about the dy dx, and I guess my t at the end of my word went to a d. So we want dy dx. Well, how do we find that? We would need to take the derivative with respect to x of this whole thing. And some of these things you know the derivative already. Do you know the derivative of x squared? Right? That's just 2x. So unlike the video, I do not put a dx after that. So the video we just watched, they put a dx after that without explanation and just said this is the way you do it. I don't like that. I like to have an explanation. So I know the derivative of x squared, it's dx. What is the derivative of y squared? And this is where, if you had y by itself, do you see that this would be a chain rule? This whole thing would be inside the squared. How do you do a chain rule? You do the derivative of the outside function, so the 2 would come out in front. You would keep the inside the same, multiplied by the derivative of the inside. Now, if you could get y by itself, and you took the derivative, you would get dy dx. Who knows what it equals to? But that's the idea being here, I write dy dx. Because the derivative of y is the derivative of y. dy dx is the derivative of y. So here in my chain rule, I did the outside function, the 2 came out in front, keep the inside the same y, and then you have to multiply by the derivative of the inside. I don't even know what it is, but I'm just going to write dy dx, because that's the derivative. And then, do you know the derivative of 16? Absolutely. It's 0. And now, we just need to get this by itself, because that's actually what we wanted to find. We wanted dy dx, now it's in the equation. I can rearrange this equation by moving the 2x to the other side, and divide both sides by 2y, and I'll get negative x over y. In implicit equations, your derivative depends on not only the x-coordinate, but also the y-coordinate. Now, I like this example because I can actually look at the equation of a circle solved in one part of it, right? This equation, plus or minus the square root of x squared, actually is, here's our circle with a radius of 4. The plus side is this green section above. The red side here is the negative side. So I'm going to look at just one of them. Maybe I do the plus side. I'm going to split my page here, and I'm going to imagine if y equaled the square root of 16 minus x squared, or y equaled, put it in brackets, 16 minus x squared to the half, could you do the derivative? Absolutely. It's a chain rule. What do we do with the chain rule? Derivative of the outside function. Do you see that my 1/2 would come out in front? And I would keep the inside the same to the negative 1/2, multiplied by the derivative of the inside, which is negative 2x. Can you see that this 2 and this 2 would cancel out? And if I wanted to, I said I could move this down to the bottom, right? And moving it down to the bottom would give me the square root of 16 minus x squared. Because I have a negative exponent of a half, that brings it down to the bottom. A half makes a square root. I'm going to highlight something here. And I'm going to highlight it right there. Do you see that that's your original equation now on the bottom? So another way I could write this is that the top was negative x and the bottom was y. And it's exactly the same as what we found with implicit differentiation. So you can always, if you were allowed to get y by itself, you could always do the derivative with chain rules and all of our derivative rules. And then if you notice something was the same as your original equation, you could plug y back in to that equation. The annoying thing about that is I've only done half. I'd have to also check with the negative out in front and do that one again. And you will find out you get exactly the same thing. You can rearrange it to be negative x over y again. So the idea of implicit differentiation is this. If we take the derivative with respect to x, most of the equation, like this circled in green and this circled in green, you already know the derivative of. The parts that have a y, you're going to have to do the derivative like it was, like what's the derivative of 2y? Y squared would be 2y, but then think you would have a chain rule and still have to do the derivative of y, which would be dy dx. Simplified, if you like nice and simplified things, is you do all of your derivatives with your derivative rules like normal, but whenever you have a derivative that included a y, you have to times by dy dx afterwards because you have to do the chain rule. So what does this look like with a couple of examples, right? What did we do? We assumed y is a differentiable function with respect to x, even though we don't know how to get y by itself. We differentiate both sides with respect to x, and then you just need to find out what dy dx is in the end. Okay, we did this one already. We can look at this next one.
Could you do it for the video though?
I did it on the video when I did it here. That was on the video already. You wanted it officially again? I could click the boxes. So I take d dx. I actually like putting the whole thing in brackets sometimes and doing d dx like this. But that means I'm taking the derivative of each thing separately with respect to x. The first one, that's just 2x. The derivative with respect to x of y squared would be a chain rule. The 2 comes out in front, the inside function y stays the same. Then you'd have to multiply by the derivative of y, which is just dy dx equals 0. Right? Anytime you have a y in them, you'll probably have to use a chain rule. And then we just rearranged, which we did before, and get negative x over y. So if I want to find y prime in this situation, I would do d dx of everything. The easy ones are going to be the ones without any y's in them. d dx of 3x to the 4, that's 12x cubed. The d dx of the 15 is going to be 0. How do we do the derivative of x cubed times y? Well, x cubed times y is a product rule. We have to keep one the same, do the derivative of the second one. What's the derivative of y? It's the derivative of y. And you can either use the y prime notation or dy dx. Then you keep the second one the same, multiply by the derivative of the first one. One of the challenges in this question is that you had a negative sign to begin with, so it's very important that you put brackets here, because that negative is going to get distributed. Life hack. I actually do a life hack on these ones. Since the negatives cause so much problems, I just move them to the other side to make them positive, and then you won't have any problems whatsoever with negatives. So actually, if I was solving this one, I would take an extra step to do this. See how I just move things over? The negatives will cause you all sorts of issues if you're not careful. So avoid them, right? So it's a good life hack. If there are people that are negative in your life, avoid them. Then there won't be problems as well. And sometimes that's easier to say than do, but it's a good life hack. It works for calculus as well. So that's what I would personally do. Then you're never going to have to, like here, you have to distribute this negative. And if you forget that, your old derivative is going to be wrong. If you move things over to be positive to begin with, that wouldn't be an issue. d dx of 15 will be 0, and here, the derivative of y to the 7 is 7y to the 6. But then since it has a y, we have to do the chain rule, and you would get a y prime. So after all of this, I'm going to take out a green square here, and I notice there's y prime in 2 spots. I need to get y prime by itself, because that's what this question was asking for. So what I'm going to do, I'm going to distribute that negative, and then I'm going to put all of my terms with y prime on one side of my equation. Here, I'll put that green box. Here's my y prime. Here's my y prime. Now I've moved both of those terms to the same side. Everything without a y prime, I'm moving to the right-hand side. Because if you have everything with y prime on this side, can you see that you could factor it out? Right here, I took that green box, I factored it out. Kept this side the same. And then if I wanted to get that by itself, now that it's factored out, I'm multiplying by this, I would need to divide by this. So shortcut of what we're doing here. We are just doing our derivatives like normal of each term. But whenever we have a y, we do its derivative like normal. Like what's the derivative of, if you just had an x, your derivative would be 1, right? If you just have a y, your derivative would be 1, but then you'd have to multiply it by y prime or dy dx. So wherever you have a y, when you do the derivative, you do dy dx. And that's because you're assuming, what we're doing here is we're assuming we were able to get y by itself, and someone actually did the work already and found y prime for us. So if you were able to get y by itself, the derivative of y by itself would be the derivative that someone found for you. But I'm not going to write it out. I'm just going to write y prime instead. Because I actually don't know what it is. And in the end, we get an answer that says, oh, I know what the answer is. It's exactly what you found, but I plugged in y instead of what you found, which we can't actually find in this case. And we get a derivative that has two variables. And so now if you want to find the slope at a point, you'd have to plug in your x value and plug in your y value. So let's look at another one. This one, you could actually get y by itself. Does anybody know how to get y by itself? How do you get the y out of sine? Sine inverse. Okay. So y is equal to sine inverse of 3x to the 7 cos x. Did we learn a shortcut for sine inverse yet? Oh. Will we? Yes. Oh. So too many shortcuts already? So, wonderful. We can get y by itself. But we don't know that shortcut yet. So now we're stuck again. But what we can do is we could say, I can take the derivative with respect to x of both sides. Can you see that the right-hand side is something you already know how to do? Right? It's a product rule. How do we do a product rule? Keep the first one the same, derivative of the second. Then keep the second one the same, derivative of the first one. How do we do the derivative of the side with the y? Well, you do the derivative like normal as if it was an x. What's the derivative of sine? Cos. So I'd write cos y. But because it's a y, I'd have a chain rule. I'd have to multiply by the derivative of the inside. The inside is y, and the derivative of y is the derivative of y, which is why we write dy dx. This is the only place I have dy dx. So if I want to get that by itself, can you see that you could divide both sides by cos of y? So the idea of implicit differentiation is instead of not wasting, right? But sort of. Instead of wasting your time getting y by itself so you can take the derivative, we just assume you could do that and assume the derivative exists and work with that to get dy dx by itself. I mean, technically, I'm going to go and do implicit differentiation for something really simple. All right. If this question said, find dy dx, you already know the answer is 2x. That's from our last unit. No problem there. But if I wanted to, I could do implicit differentiation of this. I could take d dx of this whole thing. I could do the derivative of each one by itself. What is the derivative of y? The derivative of y is the derivative of y. It's dy dx. What's the derivative of x squared? It's 2x. What's the derivative of 0? It's 0. I get the same answer. But now I'm using implicit differentiation. Okay? But if you wanted to find the derivative of this one in the old way, you would have to first get y by itself, right? Six x minus 1. If I want to find it the new way, derivative of y, dy dx. Derivative of x, 1. Derivative of this, 6x. Could I get this by itself? Absolutely. Would I get this? Absolutely. So sometimes it's nice to see implicit differentiation in the stuff we've already done and to realize it's actually the same idea. But now we're just taking the derivative with respect to everything, and we're saying, I just want to rearrange afterwards rather than rearrange at the beginning. Especially when rearranging at the beginning, like in this last one, gives me a sine inverse. And we haven't learned the shortcut for sine inverse yet. But it's okay, because I can still do it without the shortcut for sine inverse and figure that out. What do you have to do if you don't know a shortcut? You'd have to use the definition of the, oh my goodness. Plug in the x plus h. No, definitely don't want to do that. Like the shortcuts, right? As soon as you start complaining that there's too many shortcuts, then I'm just going to make you do definition of derivative for everything. And then you'll see like, oh, it's okay. I like the shortcuts. All right. We will leave the rest